some of the waveforms are shown on this slide, the others will be shown on the next slide. So these three, that's the cluster, that's the NRZ group, and this is the RZ group, these three waveforms, and the other two groups are on the next slide. So when we go on the next slide, you will see them. So what you need to understand about every waveform is the principle of working or the principle of construction of the waveform. So let us start with the first one, NRZL, the non-return to zero level. So this is a very simple waveform where a positive voltage plus V that represents bit 1 and minus V that represents bit 0. So we have considered an example sequence here of 1011, 000, 1101. This example sequence is used to construct the waveforms of all the PCM waveform types that we will study. So according to this sequence, if these bits have to be represented by NRZL waveform, this is what the waveform will look like. So plus V for 1 and minus V for 0. So that is NRZL. So it is very much simple and clear, and I hope you will not have any confusion in this waveform at least. Okay, going on to the next one, NRZM, where M is for mark. This PCM waveform scheme is also known as differential encoding, and its principle of construction is that whenever you have a bit 1, there is a change of polarity, and when you have a bit 0, there is no change in the polarity of waveform. So based on that, when you consider this, so the starts are assumed without any specific order, so the starts are random. But remember the principle of construction, that there is a polarity change whenever there is a 1, and there is no polarity change when there is a 0. So at the start of here, the polarity is plus V, so that means probably the polarity here was minus V, because when a 1 came, so the polarity changed. So it was probably minus V here, and when this 1 came, the polarity changed, it went to plus V. And then when a 0 comes, there is no polarity change. When we have a 1, as you can see here, when we have a 1, there is a polarity change. Once again, at the end of the bit interval, we have a 1, so there is a polarity change, and here there is no polarity change because we have a 0. Here we don't have a polarity change because we have a 0, and so on. So that is how NRZM has been constructed. And the third one is NRZS. NRZS uses the same principle as NRZM, but for 0. So that means there will be a polarity change when there is a 0, and there will be no polarity change when there is a 1. So as you can see here, whenever a 0 comes, we have a 0, so we have a polarity change. We have a 1, so no polarity change. We have a 1, so no polarity change. We have a 0, a polarity change, and so on. So that is how the NRZS is constructed. So the NRZ schemes, they follow this principle that they stay at the level until there is a change. So they don't go to 0. There is no 0 involved in them. So this was the NRZ group. Now we move on to the RZ group, return to 0. So there are a couple of things you need to remember about the RZ group. The first thing is that the pulses are half bit wide. So the pulses are of half bit duration, as you can see here in all of them. The pulse width is half of the symbol duration or bit duration. That's the first thing you need to remember. And the pulse, it returns to 0 after half bit duration. Whatever the level of the pulse is, it returns to 0 after its duration is complete. That is why they are known as return to 0. So when the half width is complete, it returns to 0. So please remember that. Okay, so these two things, half bit wide pulses and returning to 0 after half bit duration, that applies to all the three of them and to the whole group. Okay, now coming over to the first type, which is unipolar return to 0. So sometimes the names also guide you. So unipolar means having one polarity. So it has a plus V and a 0. It doesn't have a negative voltage. It is unipolar. So whenever we have a 1, we represent it by plus V, and whenever we have a 0, we represent it by 0 volts. And because it's return to 0 scheme, so for the 1 we represent it by a pulse of plus V, but after half time it returns to 0. For a 0 we represent it by 0 volts, 1 we represent it by plus V, but it returns to 0 after half time. Similarly here, this 1 is represented by plus V, but after half time it returns to 0, and for 0 it stays at 0, and so on. So that is how the unipolar RZ is constructed. And then the next is bipolar RZ. So as the name indicates, bipolar means two polarities, and it is returned to 0. So one polarity for one bit, the other polarity for the other bit, and after half time it will return to 0. So in principle, bipolar RZ looks very similar to NRZL, but with half bit pulses, with a return to 0 introduced. So for 1 we have plus V, for 0 we have minus V, just like NRZL, but the pulses here are of half bit duration, and the pulses return to 0 after half time, as you can see here. So that is bipolar RZ. And then the last of the RZ group is RZAMI, return to 0 alternate mask inversion. And for 0 it is 0, as you can see. Just acknowledge all the zeros here, they are represented by 0 volt level. So for 0 it is 0, and for 1 it has alternating polarities of plus V and minus V. So when the first one comes here, for example in this case, for the first one it is plus V, for the second one it is minus V, for the next one it is plus V, for the next one it is minus V. So plus V, minus V, plus V, minus V for all the ones, and 0 for 0. So because it is changing polarity, it is known as alternating. So it is alternate mask inversion. The pulses are half, they return to 0 after their time is complete. But please note here that in RZAMI only, the half pulse does not start from the start of the bit interval. The half pulse is there in the middle of the bit interval. So if this is one bit interval, 25% space here and 25% space here, that is not utilized, and the middle 50% of the bit interval, that is where the pulses are. So the pulses do not start from the start of the bit interval. That is what you have to remember about RZAMI. So this is the end of the RZ group. Now we will move on to the next slide to discuss more PCM waveform types. So the next group is that of phase encoded group. The first three waveforms, they are the phase encoded group, and in principle the bit duration is half bit. So in principle we have half bit duration pulses, which under certain conditions change that behavior. Anyways, so we have the biphase level, the biphase mark, and the biphase space, these three in the phase encoded group. So first of all, looking at biphase level, which is also known as Manchester coding or Manchester encoding, and the principle of construction is that there is a half pulse, so the polarity is plus V during the first half. There is a polarity of plus V during the first half of the bit interval when we have a 1, and the polarity is plus V during the second half of the bit interval when we have a 0. So when we have a 1 in the first half of the bit interval, so this is the whole bit interval, so in the first half the polarity is plus V when we have a 1, and when we have a 0 in the second half the polarity is 1, and other than that the polarity will change. So as you can see here, for the 1 the pulse level was plus V for the first half, and because we have half duration pulses, so after half time is complete it changes its level, and then for a 0 we need to have a plus V in the second half, so we need to have a plus V in the second half, so it remains at 0 and then changes here. And then for a plus 1, for a 1 we have a plus V in the first half, so it carries on at plus V, and then after half time it goes to minus V, and then again the next bit is 1, and for a 1 we have a plus V in the first half, so it goes to plus V in the first half and then comes to the other polarity. And the next one we have 0, and for 0 we have a plus V in the second half, so as you can see here. So that is how the biphase level waveform or Manchester coding waveform is constructed. And now coming over to biphase mark, there is one thing to remember first, that there is a transition at the start of every bit interval. So there is a definite transition at the start of every bit interval. So if you notice here, there is a transition or a change of polarity at the start of every bit interval, irrespective of where it is, where it was, there is a transition. That's the first thing. And the second thing is that there is a half time transition when there is a 1, and there is no half time transition when there is a 0. So we have transitions at the start of every bit interval, that's there all the time, and then if we have the bit value as 1, there is a half time transition, and if we have a bit 0, there is no half time transition. Bit 1 half time transition, bit 1 half time transition, bit 0 no half time transition, no half time transition, and so on. So that is biphase M. And we know that the mark and space schemes, they work with the same logic, but in one scheme the logic is for binary bit 1, and in the space scheme the same logic is applied for 0. Okay, so for biphase space, what we need to remember is that once again there is a transition at the start of every bit interval, that is there, and there will be a transition at half time if there is a 0, and there is no transition at half time when there is a 1. So you can verify that if you look at all the half time transitions, they are coming when we have 0, and there are no half time transitions when we have 1s, as you can see here. So that is biphase space. And then we have the delay modulation, which is also part of phase encoded group. Okay, and this delay modulation is also known as Miller coding. And the principle of construction is that we have a transition at half time when we have a 1. So first let's see that all the half time transitions we have a 1. Okay, so these are all the 1s. So we have half time transition for 1s, and there are no half time transitions if there is a 0. That is understood. Now if there is a single 0, we will not have a transition. If there are consecutive zeros, that means a 0 followed by a 0, there will be a transition at the time when the first 0 finishes and the second 0 starts. There is a transition at the start of the bit interval, or you can say at the end of the first bit interval and the start of the second bit interval, when two zeros are together. So half time transitions for 1s, no half time transitions for zeros, and when there is a single 0, nothing at the bit interval, as you can see here. When there are consecutive zeros, for example here we have consecutive zeros, then where the first zero is ending and the other is starting, there is a transition. Once again we have two consecutive zeros here, so at their boundary there is a transition. See, so these boundary transitions only take place where we have consecutive zeros, otherwise we don't even have those boundary transitions also. So that is Miller coding or delay modulation. Then the next is die code NRZ and die code RZ. So die code non-return to 0, that is based on the logic that if the next bit is different from the current bit, there is a transition. Okay, there is a change of polarity if the next bit is different, and if the next bit is the same, then it goes 0. So rather simple logic. If the next bit is different, change polarity. If the next bit is same, go to 0 if not already at 0. So let us have a look. Here, assuming that we started with -v for this bit 1, the next bit is different, so change of polarity, and then the next bit is different, change of polarity. Now the next bit is the same, so go to 0. Now the next bit is different, change polarity. Now the next bit is same, go 0. Next bit is same, 0. Next bit is different, change polarity. So as you can see, it is also keeping a record of the previous polarity used, so that when the time comes, so it knows that which polarity to take. Okay, and whenever the next bit is the same, it goes 0, and so on. So this is die code NRZ. And die code return to 0, it has the same logic, but it returns to 0 after half bit duration, if it is not 0 already. So as you can see, we started with this polarity, and after half time it goes to 0, and next bit is different, so a different polarity, and then after half time it goes to 0. Next bit is different, change of polarity. Next bit is, and then after half time it goes to 0. Next bit is same, remains at 0. Next bit is different, change polarity. After half time it goes to 0. Next bit same, 0. Next bit same, 0, and so on. So that is the principle of construction of die code RZ. So basically that completes our discussion of the most commonly used PCM waveforms, and we have discussed 12 waveforms in total, and I hope now you understand the principle of working of all of them. Now there are different factors according to which we can compare all these PCM waveforms, so I'll discuss them here. So we can compare them on the basis of different factors. The first of them is DC component. So some of the waveforms, they inherently have a DC component, while the others are not expected to have any DC component if the number of ones and zeros are equal. So for example, the first waveform, if you consider that NRZL, and if you assume that the number of ones and zeros are equal, so what will be the average value of that waveform, or the DC component of that waveform? That will be 0. Okay, so some inherently do not have a DC component, just like NRZL, but some have a DC component. For example, unipolar RZ, if you try to determine its average value or DC component, it will not be 0 unless all the bits are 0. So that's the first factor. Then the second factor in which they can be compared is internal clock. So some schemes have an internal clock built in, and some schemes they don't have an internal clock built in. For example, if you consider biphase level or Manchester encoding, there is an internal clock built in that coding scheme, because there are transitions at half time. Always there are transitions at half time, so there is an internal clock built in it. So whenever there is a transition, we know that we are talking about the next bit. Whenever there is a transition, that means we are talking about another bit. So if we count the number of transitions, all of them which will be occurring at half time, we know how many number of bits there are. So we are able to generate a clock, or determine a clock, or we can determine the frequency or the bit rate So there is internal clocking present in some of them. I'm giving you one example each, but there could be other examples also. And then another factor is error detection. So for example, in some schemes you have error detection, like the duo binary schemes, you have the error detection built in. So because you know the working principle that if the next bit is different, yes, there must be a transition or a change of polarity, and if the next bit is same, then there should be zero pulse. But if you notice that it is not doing either of them, so it is not transitioning to zero, or it is not transitioning to other polarity, then you know that there is some garbad, and probably error has been there are errors in communication. And then we have polarity inversion protection. That means that if accidentally the polarity of the wave changes, do we end up by decoding the right bits or not? Okay, so that is not there in all of them, but for example, if you consider RZAMI, okay, RZAMI produces half pulses for ones only. There are no pulses for zero, and there are alternate polarity pulses for ones. So even if the polarity is reversed, we know that wherever the pulse comes, that represents a 1. So even if the polarity is reversed, you will still end up with the right decoding. So that is polarity inversion protection. And then we have noise immunity. Some schemes have more noise immunity than the others. So generally in those schemes in which the levels are far apart, they have a greater noise immunity than those schemes in which the levels are closer together. So plus V, minus V, they are further apart than plus V or 0, for example. So some have a greater noise immunity than the others. Then another factor is that of bandwidth. We have already discussed that the narrower the bandwidth, the more is the narrower the pulse, the more is the bandwidth requirement. So some of the schemes have narrow pulses. Some of the schemes have pulses changing polarity very frequently. So all such schemes they have a higher bandwidth requirement than those schemes where either the pulses are wide or the pulses do not change very rapidly. And finally, we can say that some schemes are balanced and some are unbalanced. This is somewhat linked to the first point. So balanced schemes are those which are symmetrical about 0. So generally all the bipolar schemes, they tend to fall under this category, whereas the unbalanced schemes are unipolar schemes. So these are some of the factors in which we can compare the different PCM waveforms. Now we are discussing the concept of Emery communications, and the concept, you've already been introduced to this. The concept is that we send multiple waveforms denoted by M, where M is greater than 2. Okay, so we choose between one of the M symbols instead of choosing between only two symbols, one which represents 1 or one which represents 0. So that means we are talking about symbols having more than 2 levels. Okay, so the waveforms that we choose, the multiple waveforms, they may be different in their phase, amplitude, or their frequency. The advantage obviously is that we can send more information at a time. We can send more information in a single waveform or in a single symbol, and the disadvantage is that either we will need more bandwidth or we have a lesser margin against noise. So okay, let's have a closer look. So we are considering an example of a 4 ARY amplitude waveform here, where as you can see the pulse has 4 different amplitude levels. So we can say we have 4 symbols, and as you can see in the combinations, every symbol represents a unique combination of 2 bits. So every time we send a symbol, we are successfully sending 2 bits. So each symbol sends 2 bits, and but the drawback is that deciding which level is correct, it gets harder due to fading and noise. So if the levels are close, there are a lot of levels, then they are close to each other, and even a little bit of noise or fading that can cause the receiver to make errors. So in that case, as we increase the value of M, the receiver needs a better signal to noise ratio to achieve accuracy and to improve its error performance. So we can also use Emery amplitude shift keying, so whereby we send multiple amplitudes to denote different signals, and we can have different options as shown here, plus minus P, plus minus 3P, plus minus 5P, and so on. So we can have a typical signal configuration with multiple amplitude levels. We can also have multiple phase. So for example, shown here is binary phase, where we are using two phases, one to represent binary 1 and another phase to represent a binary 0, as shown here in the first half of the slide. So this waveform, for example, this phase 0 degrees, that represents binary 1, and this 180 degrees that represents a binary 0, which are indicated by these two crosses here. But then we can also increase it from binary phase shift keying to M level phase shift keying, and for example shown here is M is equal to 8, so we can have 8 different phases. Each phase represents so each cross here, that is basically a symbol, and each symbol now represents a combination of 3 bits. So whenever we successfully transmit a symbol, we are actually transmitting 3 bits. So if the symbol rate is 1 symbol per second for both of them, so when we transmit one symbol in this case, so we are basically transmitting 1 bit per second. But if the symbol rate is 1 symbol per second and we are transmitting a symbol here, then basically our bit rate is 3 bits per second. And then that's even a higher level, where this is a higher level modulation known as quadrature amplitude modulation, where we are using 16 symbols. So every symbol now represents 4 bits. So if the symbol rate is 1 symbol per second and we successfully transmit 1 symbol per second, that means we have transmitted 4 bits per second. And this can even continue even higher, so the value of M can be higher, but as we discussed, there are advantages and disadvantages. The advantage is obviously our bit rate is increasing, but the disadvantage is that the points are coming closer together, and when these points start coming closer together, we have lesser margin for noise and fading. So as I said, as M increases, it is harder to make good decisions and more power is required, but the advantage is that more information is packed into a symbol, so data rates can be increased. So generally what we can say that if we want to achieve higher data rates, we will need more power. So this is especially applicable at shorter distances, so we can achieve a higher SNR and we can get good results. So now we come to the next block in our digital communication system, which is that of channel encoding, as you can see here. So we have discussed about source encoding block, and now we are starting our discussion of channel encoding. And the main concept of channel coding, which includes encoding and decoding, the main concept is to combat channel effects. So what is channel coding? It's a class of signal or sequence transformations which are designed to improve the communication performance by enabling the transmitted signals to better withstand channel distortions such as noise, interference, fading, etc. So we are preparing our signal beforehand. Before going into the channel, we are preparing it for the ill effects of the channel. So we know while it goes through the channel, it might get affected by noise, interference, fading. So how we can better prepare our signal to combat those channel effects? So this is like the vaccine. So channel coding, generally channel coding techniques then can be divided into two major classes. Either we do waveform coding, in which we change the signal design, or we do structured sequence. So in our bit sequence, we add some extra bits by adding redundancy. Redundancy here refers to extra bits. So these are the two major categories of channel coding. So what is waveform coding? It deals with transforming waveform into a better waveform. which is more robust to channel distortion. So hence it improves the receiver or the detector performance. So there are some examples. For example, going for antipodal signaling, signals which are 180 degrees apart, or orthogonal signaling, signals which are orthogonal to each other, 90 degrees phase difference, or bi-orthogonal signaling, which is the opposite of orthogonal, or emery signaling or trellis coded modulation. These are all examples whereby we transform the waveforms. And the second approach is structured sequence. And what are structured sequences? We transform our sequences into better sequences by adding a structured redundancy or redundant bits. So we add redundant bits in a controlled or structured fashion, and those bits are basically used to detect or correct errors, and hence once again we improve our overall performance of the communication system. And for example, so we either use linear codes or non-linear codes, and at undergraduate level among the linear codes we will be basically looking at Hamming codes, and among non-linear codes we will be looking at convolutional codes. And these are the examples of error correcting codes basically. So my dear students, that brings us to the end of this lecture, and inshallah see you in the next lecture with further details of channel coding. Thank you.